Hello. Where did we stop? In the first part, we talked about what influence a PID controller has, or what influences on the closed loop the PID control elements can have. And to get that, or to sum that up, or like get everybody on the same page, I want to redo a quick summary, not really summary, a quick wrap up in OneNote, right? So we started to actually closing the loop, right? Started closing the loop. And I just want to take a couple of minutes what that actually means in terms of system dynamics, right? We have a system G of S, and we said we're going to design a controller R of S, right? And we have an output, and we have a reference. Sorry, we have a control error, we have a control input. So obviously we have learned when we talked about system dynamics that G of S is our system we want to control, right? Okay, and this G of S has poles and zeros. And we know that when we calculate the poles, they're going to be conjugate complex, then it's oscillating. If they're real, our system is not oscillating, right? So far, so good. So obviously, R of S can also have poles and zeros, but they are our choice. Actually, I write your choice, right? So you can decide how the controller looks like and what poles it should have. But how is the question, right? So we select this R of S. So that the closed loop, which is this guy here, behaves as we desire. So what does this what we desire actually mean? Well, it means that we have design specification, right? Very simple one, you could say, okay, my G of S has a steady state gain of 0.7, I want to have it 1, right? So what does this design specification mean? First, we can have design specification, for example, on the steady state behavior. Right? Meaning that is that the static gain of T of S, or T0, is not equal the static gain of our open loop, right? I mean, this should be kind of clear, or the static gain, let's write it this way, static gain G0, right? So we are changing how the system behaves in the closed loop. And obviously what we also change is we change the dynamics. Meaning that the poles of T of S are not equal to the poles of G of S. We use the controller, this guy here, and we use the feedback, this feedback here, to change the dynamics and the steady state behavior of our T of S, right? I mean, this should be kind of clear. It's just like bringing everything in perspective, what we are doing, right? So you have a system, you want to change that system. You want to change the steady state behavior. You want to change the dynamics. You want to change the steady state behavior, for example, of the complementary sensitivity function T. You want to change the steady state behavior of your disturbance sensitivity. Maybe you want to change the initial value of your control sensitivity. So these are all design specifications you have, right? So the question remains how to select R of S so that the specifications are met, right? So, and what we have learned in the first part today, we can select a structure, or we have to, right? So is it a P controller, is it a PI, a PD, and so on, PID, whatever. And if we have that, then we have to select the numerical values, right? And this is what we're going to do now. So technically, your design approach for a controller is the following. You need to do the modeling, right? This is step 0. Sometimes, especially if you do aircraft control, you get a model, and the second part is you need to design the controller, you need to design the controller, and hopefully you have design specifications. If you don't have any design specification, you are basically free to choose them. But this is usually the way, right? It's also the way as we did it in the lecture. We first talked about our G of S, our system, and now we're talking about the control design. And here you go for the structure of the controller, and then you decide for the numerical values. But we'll see. This is the basic approach. Another approach is that we do the structure selection and the numerical selection in one shot, right? But this comes later. So this brings us to the next part of the lecture, namely the controller design itself. So how can we end up with a nice control behavior so that the closed loop behaves as we want? Okay, I'll jump over. So a new chapter. So, and here's our intermediate result. We have covered how a PID controller looks like, what elements are doing. We know how to analyze the closed loop. We've actually talked now about how do we choose the structure for a given problem, for a given design specification. And now the open question is, how do we ultimately choose the numerical values of our controller, right? And to be fair, there are numerous design strategies for controller. All of them have pros and cons as usual. And today we're going to start out with a group of so-called heuristic methods, and they are like Daumenregeln. So let's start even further. Basically, for control design, you have two options, right? The first option is the mathematically easier one, but it's not so sophisticated. The most easiest version to design to get to the numerical values is simply do an experiment, right? So what you're doing is you take your espresso machine or whatever, your car, and you do an experiment. And based on that experiment, by just looking at the output of the system, you decide on the numerical values. And some smart people have done this before already. So this is what we're going to do in the first half an hour. For that approach, you don't need any mathematical model, right? Not any one of those approaches actually makes a very rough approximation of your system by a PD1 with some time delay. The problem is that each system is very, very different, right? A car behaves different, like an espresso machine, a robot, and an aircraft. So it's kind of hard to get all these systems in one rule of thumb, in eine Daumenregel. Yeah? You can do it, but it's going to be a very rough approximation of a good controller. And this is why, especially for aircraft control and for car control as well, we are basically doing a model-based approach, where the first one is an experimental-based approach or heuristic methods. The second one is a model-based approach. That means we take an intermediate step and first create a mathematical model, like an ODE, a transfer function, a system of our hardware. And taking that hardware, we're designing the controller, right? So I give you a transfer function, you design a controller for it, you take the controller, you put it on a piece of hardware, and you test it, right? This is a so-called model-based approach, which is unavoidably in like any safety critical system, right? You don't want to go on an Airbus and do a control design where you first need to crash it, right? So you have to make sure when the pilot sits in there, that your controller is not crashing the aircraft, right? The autopilot should not crash the aircraft. Otherwise, your boss will not allow you to test this controller. So you go ahead and you build a mathematical approximation of the aircraft. For that one, you design the controller, and when you're sure it's going to work, or you're never going to be sure, but 99.99% be sure that it's going to work, you then take it on the aircraft. You're not going to do an experiment. But for easier systems like the espresso machine, you can actually do this heuristic method. Actually, Knorr-Bremse, for example, I think is also doing this heuristic methods for braking systems. I'm not sure if this is not safety critical, but anyway. So, heuristic controller design. So what, again, let's do, we have two options, right? You don't need to write it down, I just want to make it clear. First, heuristic methods based on experiments, or model-based. Methods based on a model, or based on based on model. That's why it's called model-based, right? Based on mathematical description. So here you really work on your experiment, like this robot here, right? Here you really tune the controller live, so to say. And here you first build a mathematical model, G of S, and then you plug the controller around first on paper, and then you see if it's working. And then you go to the hardware. While here for the heuristic methods, you really just take the controller on a piece of electronic equipment, and then you build the controller directly into your system. So you never take that immediate step of doing the mathematical modeling of your system, right? So you really work on the hardware. You go to the lab where your robot is standing, you plug in the controller, you say, okay, maybe proportional controller with 500 is good. You turn the controller on, it smashes you, you know it's not good. Maybe the gain was too high, you set it to 100. And so this would be a heuristic method, right? So just trial and error, basically. And to avoid fully trial and error, you're using heuristics, right? So a lot of, you can, by very simple approximations of your experiment, you can already come up with a very good value, maybe 110 or something, I don't know. While for a model-based approach, you completely say, I take the robot, I do a mathematical modeling, and then I leave the experiment behind, and I do the control design on paper, in Simulink, and so on. And when I know it's working, then I'm going to go back, and I know a value of a proportional controller of 105 is perfectly fine. Obviously, there's still some fine-tuning then to do, but it's a much better approximation as all these heuristic methods. Okay, obviously you can also do AI if you want to, but yeah, don't do it with an aircraft. Okay, so, and the first method I'm going to show you is the so-called Ziegler-Nichols methods. The idea here is that you first look for a PID controller structure, right? So you say basically, okay, I have a proportional system. I know it's proportional. Actually, you don't even have to fully know it. And you say, okay, I need a steady state accuracy, maybe an integral controller with which is a little bit faster. So a PI controller would be good, right? And when you have the structures, rules of thumb are then used to set the numerical values without mathematical modeling, right? So, and why it's called Ziegler-Nichols, well, these were two guys which did a lot of controller testing and kind of came up with these methods. So, the first problem already, it is really limited to the control of stable systems which are non-oscillating. So it's basically we are talking about PTN behavior or PDTN behavior, and which are non-oscillating, right? So think of an aircraft, pitch dynamics, as you covered or still cover in flight mechanics, is always oscillating, and a self-driving car has always an oscillating behavior, so it's unsuitable for that. But like process engineering told you in the morning, process engineering has a lot of delayed processes in. For these systems, this method actually works pretty nice. So when you look in the literature, there are various variants of it. I'm only going to show you two of those. If you kind of get the idea here, it's enough, and it's not really big science, right? So it's really, easy. So the first method is actually trivial. You take your experiment, right? So you take your robot arm and you plug a proportional controller around P, right? Like you did with the espresso machine, so to say. And then you choose a very low value for that proportional gain, and you do the experiment. And let's say that your robot arm should move from A to B, and it moves there. If it's proportional, it will not fully move there. We know that by now. And then you turn up the gain. You turn it up. So it's going to get faster, and the speed, when speed comes, also oscillation comes. And you turn that gain up until it gets unstable, until the point it's just still stable. So you go to the border of stability, right? And this is called the critical gain, right? You've seen it with the espresso machine. When you put the gain too high, you're actually getting unstable. And obviously there is exactly this one gain where it's not stable and not unstable, but it's on, your poles are on the imaginary axis. So you're neutrally stable. You're looking for that sweet spot, so to say. Okay, this is your critical gain. And the only thing what you then do is, okay, instability in a linear sense will always be like, it will oscillate forever, right? And then you simply calculate the period of the oscillation, which is your critical period. And all you need is these two values. You take these two values, and from that you calculate your controller gain. And this works for P, PID, PD, whatever you like, right? You only need these two. But you see, every system will become differently unstable. So it's really hard to get only by these two parameters a good controller for all the systems we have, like for an espresso machine, an aircraft, whatever, right? So it's a very rough controller, let's say. But the main disadvantage of that method is that you need to drive it to the border of stability. Remember, we're not having a mathematical model or a Simulink model where we just turn up the gain and it oscillates in our nice plot. No, we are working on the actual robot. And driving a system to the edge of stability is always kind of dangerous because you might overload the hardware. For example, your robot could just break an arm or fly through the window or whatever, right? You really could destroy the structure. So this approach might not always be the best one because you're moving it to the edge of stability. Think of your espresso machine. If you turn the gain up until the water boils, some parts in your espresso machine might be broken because the water was too hot and some parts may be melted, right? Okay, that's why we have a second method I'm going to show you. And this method is you take your model, you do an experiment, you basically plug in a step response, a step input, and remember, we're assuming a simply PTN behavior. And whatever comes out of it, you take that answer and approximate that system with a PD1 system with time delay. So what you're doing is you take your piece of hardware you like to control, you put in a step, whatever it is, you record it on your computer or on paper or whatever. You take the response, this PTN response, and you approximate this response with a PT1 system with delay. And a PD1 system, we know that, has a gain, has a time constant, and additionally a delay. I will show you that in 2 slides. And based on these 3 values now, instead of 2, you can calculate the controller values. Okay, so these are actually these heuristic methods basically work always the same. So if you understand those 2, you're good for the heuristic methods. So let's start out with in more detail with the variant number 1. So the Ziegler-Nichols method always assumes we have a controller in that form. Right? So it's the parallel form. It's not the series form where we have a single transfer function. It's the parallel form where we have all the 3 parts individually. And the idea is, at first, to only use this a proportional gain and make that gain bigger until we have continuous oscillation in our experiment. Right? And from there on, we compute the critical, so we get to the point where we set Kp and we get such a response, right? And then what we do is we measure the period, which is T critical, and we know the gain. And based on these 2 values, we now calculate the gains we need for the PID controller. And you will see it's actually pretty intuitive what happens. If you say, and remember, we have to select the controller form in advance. Let's say we want to have only a proportional controller. Okay, we look in our table and it says, okay, Kp is equal this constant here times our critical gain, which we measured from our experiment. So you should raise the question now, well, what's Cp then? Well, this comes from a fixed table which Ziegler and Nichols developed. And I think the proportional controller is actually a pretty nice example. So remember, we do the experiment, we turn up our proportional gain in the loop until it reaches the border of stability. Our system gets unstable. So we know this Kp critical. We know Kp crit. This is the proportional gain when our system gets unstable. And what should we use as controller gain? Well, we should use this one if we want to implement a proportional controller. Okay. So it takes this critical gain and multiplies it by 50%, by 0.5. What that simply means is, or what the table says is, do the experiment, figure out what the gain is where your system gets unstable, and take this gain 50%, and this is your proportional controller. Simply. Okay. If you decide to go for a PI controller, you don't take 50%, you only take 45%. Plus, you now add 85 0.85 times the critical time period inverse times Kp, right? So what you could interpret here is, okay, because of the fact that I'm adding integral action, I have to go a little bit smoother with my proportional gain. This is why I need to turn that down from 50 to 45. Okay. Now, if you say I want to go PID, okay, you know that the PID controller actually adds some speed. So it adds some damping, it adds basically stability. Because the D term adds stability, I can also go a little bit higher with my critical gain. Right? But really, plain simple is you do the experiment, you calculate these two values, you decide which controller you take, you look into the table, and in the table you find these values, and these values are really constants Ziegler and Nichols already determined for us. That's it. I'm going to do an example. I'm going to do an example in just a second in MATLAB after the second variant that you actually see what I mean. Okay, again, the problem with this method is really that you have to drive it unstable, right? And there are a lot of systems you actually do not want to drive unstable to calculate these two gains. And this is where the second method is a little bit, let's say, not so hard on our physical system. Because in the second variant of the method, we are simply doing a step response, right? So when you have your espresso machine in front of you, you say, okay, I'm putting in 0.25 kilowatts and I'm measuring the output signal, the temperature, and I'm recording it with a computer, or I print it out, whatever, right? So you don't need to drive the system unstable. So I think this method is probably best explained with an example, I think. And as an example, I have this PD5 system here, right? PT5 here. So this PD5 system has 5 poles at -1. It's basically having 5 time constant all at 1 second. And it has a gain, a static gain of 2.5. And I said, okay, I'm going to do a step response where I put in a unit step of equal 1. Obviously, you see, if I put in 1, this guy needs to go to 2.5. And there's a lot of lag in here because we have 5 lag elements. Okay? And now what we need to do is we need to compute 3 elements to be able to apply this variant of the Ziegler-Nichols method. First, we need the steady state gain. We know how to calculate that, right? The steady state gain is basically, and remember, in practice you would not have this knowledge here, right? Because you only do the experiment, you don't know that it's a PD5. You really only have this one here. I've just showing you the PD5 system that you know what's behind, but in practice, you really would only do the experiment without knowing what the mathematical model behind is, because you don't care. Okay, so you do the experiment and you say, I put in 1 whatever kilowatt, and then you record, it goes to 2.5. You immediately know how to calculate your steady state gain. It's taking this 2.5, dividing it by the input amplitude, which in this case is 1, so the answer must be 2.5. Okay, the second step is now you go to 63%, right, of your answer, and 63% of this 2.5 is about 1.6. You go here and you note this time here. Next, you do this guy here has a S form, right? This looks like an S. And if you recall math, an S-shaped curve always has an inflection point, right? Wendepunkt. Through that inflection point, you do you construct a tangent, a tangente, right? So zum Wendepunkt und dann Tangente eintragen. Where the tangent cuts your x-axis, you note the second time, and you already kind of should realize where this thing is heading to. 63% immediately rings a bell with a PD1 system, right? So what you're doing here is you're saying, okay, I'm reaching 63% and I'm doing that tangent here. And from that time point here, well, let me change to the laser pointer. From that time point here, this system looks like a PD1 system, right? So I'm approximating this system, this PD5 system, with a PD1 system with a gain of K0 and a time constant of this here. So this is your time constant. But the problem now is, okay, it does not really start here. It starts at 0 because we put in the step here at 0. So we say, okay, this is simply a pure time delay. We say in this area here, from here to that cutting point between the tangent and your x-axis, nothing has happened, and we delay our system response. And in system dynamics, we will learn that a little bit deeper, or go into that a little bit deeper, is this then looks like an exponential function multiplied to your transfer function. Okay, so if you look closely, this is about 3.5. These are 3.5 seconds here. We've got a gain of 2.5, and we say, okay, our pure time delay is about 2 seconds. So from here to here. So, and then this is our system approximation. 2.5 over 3.5 s plus 1. So this is a simple PD1 system. And the time delay in the Laplace domain looks like this, right? So it's a 2 seconds time delay from here to here. And remember, in practice, you would write down this. You don't have this because this is your physical experiment. What's important here are mainly these 3 parameters, because based on these 3 parameters, you again decide, or you first decide which controller you want to take. You want to go for P, PI, PD, whatever. And then you calculate your controller gains. And actually, these should be small caps here. I forgot actually to replace it. So this is a small KP, small KI. Sorry for that. Need to fix that after the lecture. Okay. And again, you have these constants in there, and you can find those in the table, right? That's basically it for the Ziegler-Nichols. I have actually 2 more slides. Now, 1 more slide where we're gonna discuss the pros and cons of these methods. Again, they are pretty simple, although it might look a little bit full in a short lecture. But actually, there's nothing really big math behind, right? They just did a lot of experiments and said, okay, it used heuristic to come up with this rule of thumb. What I want to do with you now is to take a little bit into a MATLAB code where I actually took this system here, this PD5 system, and designed all of those controllers for based on this method and based on the first variant. So you also have this file on our Moodle server. I will go through it pretty quickly. If you're interested you can simply download it and look into it. What we do have is our plant is a PD5 system, right? But actually we don't know that it's a PD5 system. So this is the clue of these heuristic methods. We don't care. We just have the hardware in our laboratory or in our company, and we do the experiment, and based on that we design the controller. So, okay, let's start out with this first variant, which is based on this maximum gain. In German, you would say Stabilitätsrandmethode. In English, you just call it based on the maximum gain, because the maximum gain which you need to drive your system to instability. Okay, so the blue line, this is your open loop system response. So you don't have any controller here, right? We know that. That's what you have seen in the just in the lecture. Around that system, I'm doing a proportional controller. So I'm closing the loop with a proportional controller, and the first shot is this orange one. So clearly this orange one is far away from getting unstable. Well, not so far away, the damping is already low. And then I started to increase the gain, and you see this yellow one is also not unstable because the oscillation decays. The magenta one has still decay, and I would say the green one finally remains, the oscillation remains, right? So this is the sweet spot where our system just gets neutrally stable. And I did it by hand, and I came up with a value of 1.15 for this critical gain. Well, this was just for fun. I did a bisection algorithm just to see if I did it correct. If you do it really mathematically, you come up with a gain of 1.1538. So I actually came pretty close by just tuning it by hand. Okay, so I have you have the critical gain, and the next step is you need to calculate the period of this green curve, right? So of this oscillation. So this is again the green curve, now it's blue, with the controller gain of 1.15. And if you measure it by hand, right, really zoom in, I got to a value of 8.5 seconds, right? Also, just for fun, I did a computation, and it turned out to be, so this is the exact value. This is my value by just looking at the plot, right? And the exact value would be 8.65. So it's, as the whole thing is an approximation anyway, it doesn't matter. So I mean, 0.15 seconds away, yeah, it's a rule of thumb anyway. Okay, based on these two things, we now can compute the controllers. And again, I said, don't be misled by this case here. I changed this semester to small caps, to small letters. Anyway, you have to decide which controller you want, right? You want P, PI, PID, and based on that, you take these values and you calculate the gains. Just for fun or for comparison, I computed all 4 controllers and I closed the loop. So the blue one is obviously just the system itself. And then you have the 4 controller versions, right? What we see for the P and the PD, it is not steady state accurate, right? This is what we would expect because we don't have an integrator in the controller. Where the PD compared to the P is a little bit faster, the green one and the orange to the orange one. And using the PI and PID, they are accurate where the PID is faster than the PI, right? So again, as expected. However, I would not call this perfect controlled behavior. They are definitely oscillating quite some bit, right? So I'm not sure if you would be satisfied with such an oscillatory behavior, right? However, this control method gives you a good starting value, and now you could say, okay, I want to have less oscillation, so probably increase a little bit the D term because this guy usually damps your system, right? But you already have nice starting values for your controller, because otherwise you don't know if the value is 1 or is it 1,000 or it's 1 million, right? And based on the scaling of the system, it really can be anything. So based on this method, you already get good initial values. You can start tuning your controller and fine tune it. You don't need to have to cover the whole number space, just a very small one. Okay. Then the second variant was where we don't drive our system unstable, but we do a PD1 approximation, right? So this again is our PD5 system, the blue one, and in reality you would only have this blue line. And then what you do, you compute the controller gain, not the controller gain, you compute the gain of your system, which is 2.5. You go to 63%, you measure that time, which is the approximation of your time constant, and you calculate the time delay here from here to here. So, I mean, I did that by hand, I did it mathematically, it really doesn't matter. I think this plot is the important one. This plot actually, in reality, you would not, you only calculate those three gains, those three parameters, the time delay, the time constant, and the gain. But what the method actually does is, the method makes an approximation of your system with a PD1 plus a time delay. And this is how this looks like. The blue one actually is your real system, and the green one is the approximation, right? Nothing's happening in this pure time delay, and then you simply have a PD1 system behavior. And what the method does is, it says it basically computes an optimal or kind of optimal controller for the green one, but you already see that you have some error here. Because of that error, the controller will have some deficiencies. Or differently said, the better this green curve fits your system, so the better your system is really a PD1 behavior, the better will the controller be. But obviously, as you don't know, as you're just doing the experiment, it's a matter of, again, trial and error. So this method, again, gives you good starting values where you can start fine-tuning it. Okay, anyway, here it's basically, again, you have this table, you compute the gains, and this is actually what's important here. These are the three controllers. Interestingly, they did not decide for a PD controller here. I actually never figured out why this second method does not provide you PD controllers. Okay, again, P controller not steady state accurate. PI, PID are steady state accurate because of the integral gain, and the PID is a little bit faster. But again, here you would hope, I hope really you agree with me that this guy might be oscillating too much, and you need to do some fine-tuning of your controller gains. However, if you really don't want to do any mathematical modeling, this could be a way to design a first controller, right? Okay, that's all for the heuristic methods, actually. And that actually also concludes our story here, because now we actually know already a first method how to get to numerical values of our controller, right? We introduced two heuristic methods, very simple methods, how to get to numbers in our controller, numbers we can put on the hardware chip or on a microcontroller and let our system run. However, what are the good things on these methods? They are simple and they are fast, right? You do need an experiment, but you're comparably fast because you don't need to do any modeling. If you look into the literature or even on Wikipedia nowadays, you actually have different methods for if you want to do set point tracking. Just tracking, set point tracking is sometimes called. If you want to do disturbance attenuation, suppression, so you have different versions. But all of these versions mainly have a different table here, right? This is the main difference, while this mainly stays the same. So these are the good things. The not so good things is it's restricted to stable systems without any oscillations, right? So you have a lot of different rules for different control targets. I mean, if you're really an expert in heuristic methods, you probably know that immediately. But yeah, I've shown you two, but there are a lot more. So you need to find your way through the jungle, so to say. And the problem is, in practice, it often ends up again in trial and error, because the controller you get out is not actually the best you can get, but it's a nice starting value. Okay, so, and especially for safety critical system, again, obviously you don't want to drive your system unstable, leads you to experiment to variant number 2, but also this variant, if you design an aircraft and you say to the pilot, okay, we need to do controller tuning now, and you're going to fly it for different controllers, it's not so a good idea, right? That's why for safety critical system, where especially for aircraft, we actually prefer model-based design, where we design controllers using mathematical description. And the good news for aircraft is actually, because you're all aircraft engineers, you can actually have really good models for aircraft. And that's why the control design is actually done always with a model-based approach, right? And this is what we're going to do next. Again, now we are entering the area of model-based approaches. As a prerequisite, as it is a model-based approach, we always have to be sure that we have a model, right? You cannot do a model-based approach without a model, right? So, but in this lecture from now on, we assume we have a model. Either we do the modeling by ourselves, or if you work in a big company, you get the models from the modeling department, or whatever you like, right? So we have a mathematical model. The rest of the lecture is really analyzing that model and doing the control design. It's not about the modeling itself, although a famous control professor once said, modeling the system is 95% of the control design. The remaining 5% are just the design itself. When you have a good model, that's actually no problem. And actually that is true, because in practice you're often come up with a controller, you go into the experiment, you figure out it fails, and it fails because the model was bad. Okay. Anyway, this was just a side story. Yeah. And the first approach we're going to look at is the so-called pole zero cancellation, or it's also called pole zero compensation. Why it's called compensation, we will see in a bit. So again, it's a model-based approach. Where's my mouse? Which, therefore, we need a model. We need something like a mathematical description of our system, right? And for that system, we are going to design a controller. Okay, so let's take a look at our PID controller in this series form, right? If you look at the transfer function of our PID controller, it basically has a pole at 0 and 2 zeros, right? These guys. So we are now moving away from that form that we have Kp, Ki, Kd. We are now going to use more the form that we have 2 zeros and a control gain, right? But ultimately it's the same as you, or it's not the same, but it's the same strategy. You can either tune Ki, Kd, and Kp, or you can tune your Kpid and your 2 zeros, right? You still have 3 free parameters. Still, it's just a different form of the controller. It's just now we are thinking not in 3 gains, in the integral gain, in the differentiating gain, in the proportional gain. We are now starting to think more in 1 gain of the controller and 2 zeros. So, and instead of tuning these 3 gains, we're going to use these 2 zeros in our controller to cancel poles in our system, right? And think a moment what that means actually. We have a PDN system. Actually, this method also works pretty well for proportional systems which are just lagged. You have a PTN system and has a lot of poles. And what are these poles doing? They are delaying our response, right? Remember PD1, PD2, we said this lag on the left-hand side of the ODE makes our system actually have a little bit of this dip. It's not really jumping to the final value, it takes some time. And the poles are the reason for that. Our controller here has two zeros. What did we say about zeros? The zeros help us to accelerate the system. They actually make our system fast, right? Because they help us to react not only to the input, but the speed of the input. And this is the basic idea of pole zero cancellation. You use the fast part of your controller to cancel the slow part of your system. That's it. So you take these two zeros and you cancel two slow poles in your system, and then you have a remaining gain here, which you can set to, for example, we're going to use the often to set the damping of the system. And thereby, by this cancellation, we are actually accelerating the system. One side note, this is a PID controller, right? If you use a PI or a PD, they only have one zero, right? So if you want to draw this PI controller, looks the following. It has PI times S minus mu over S, and the PD looks R of S is equal KPD. You can name it as you like, right? This is the gain here is minus mu, right? And this is also kind of clear, should be kind of clear, because we figured if we use a PI, it has some properties. If we want to accelerate our system more, we add another D term, right? So we use two zeros instead of one. This is the same thing we have covered in this morning, just a different interpretation, so to say, because you have more zeros in your controller, and this is why your system gets faster in the closed loop. Okay, so this was the high-level series. So let's take a little bit of a closer look what it actually means. So we have a proportional system without, or actually with zeros, it doesn't matter. And we have our system, we have a gain here, and we have these poles. And the poles are ordered simply that this guy here is the slowest pole, right? If you want to draw that in a pole zero map, where you have the real part and the imaginary part, this guy would look like this with the poles. So this would be P1, P2, P3. We know that these guys are the slowest ones because they are closest to our origin. Okay? And we have a controller where we are free to choose these guys. And here this is a PID T1, so I make it actually caution. We have to consider this additional one just to make it implementable. And now we are just saying, okay, we know that these guys are the slowest ones, so we're going to take them out. So we're going to set our zeros equal to our poles. Because we are free to choose those, we directly place them over our slow dynamics and thereby cancel them out of the equation, right? Remember when I told you, when we discussed poles and zeros, at the final end I said pole zero cancellation, when does it actually appear? It appears either by modeling or when you want it to. When you say, I don't like that pole in my system, I'm going to cancel it, you can do it with your controller. Okay, but let's take a look what that actually means for the closed loop. Remember, our closed loop form looks like this, right? So we have our G of S. Maybe we should write this here. So this is G of S and this is R of S. And now we're saying, okay, these two guys here are the slowest. They make our system slow, so we take it out by these two zeros in our controller. Okay, now we want to see what happens now from R to S, because from R to Y, because these are the things we are ultimately interested in a closed loop. So we know how we compute the complementary sensitivity. It's R times G over 1 plus R times G. Okay. And now here's the trick. And please now listen carefully, because this will help you a lot. Obviously, you can plug in now both G of S and R of S. But as you have R and G multiplied here and here, it's always a good idea to cancel first, to do this pole zero cancellation in advance, because then the double fraction gets easier. So you first compute the so-called open loop, which is just R times G, right? So you take R, you multiply it by G, and then you do the cancellation. And if you have done the cancellation, then you're actually calculate that fraction here. I mean, you can calculate the double fraction here, because this is ultimately going to be a double fraction, right? Because this looks like this. Because you have the numerator and denominator of R and G. And if you don't cancel before, you always have to take these zeros and these poles with you. So I recommend always calculate the open loop. Why is it called open loop? Because it's the controller times the plant, not closed yet. So without this one, it shows up here. Cancel it and then close the loop around. So then compute T of S. If you do that, your T of S now looks like this, and you should see that P1 and P2 are missing. You took them out of the equation, and that's why you definitely have speeded up your closed loop. Right? So this is the very first model-based idea I want to show you. And we're going to apply that immediately to the espresso machine. Okay? So you take out the poles basically you don't like. So talking about taking out the poles you don't like, and this is now a new slide this semester, because I figured it kind of always is a little bit unclear. Which poles you should take out. If the controller comes with integral action, let's say PI and PID, right? So these are the only controllers with integral actions. You basically cancel the slowest poles of your system. And the system poles are the gray one. So you place, so the red one, the red elements are the controller, right? A PID controller has one integrator. So pole at 0, and it has two zeros. And you place those zeros over the slowest poles. Obviously, if you have a PI controller that has only 1 0, you only go for this one here, right? So PID has 2. If you use a PI, use the first one. In case you have a PD controller, the situation is not so fully clear. The problem here is that if you have a PD controller, you're basically not interested in steady state accuracy, right? Or you use a PD controller because you cannot introduce an integrator. So you have much more reasons to use sometimes a PD controller, and there it really depends what your goals are. And these dependency turns over which pole you need to cancel. Obviously, you could say, I'm always going to cancel the first one here. Could be true, but in practice, it's more feasible most of the time to cancel the second one. Why? this proof or this example is 2 pages long, so I'm gonna just explain it to you. The thing is, often you're gonna use a PD controller because you're not able to implement another integrator into your system. So you cannot achieve steady state accuracy. But you still want to have good accuracy. And the accuracy is better. We've learned this with a proportional controller. The bigger the gain is. And the matter of fact is that you can increase your gain even higher if you cancel the second one. If you're interested, shoot me an email. I can send these 2 pages to you. I'll show you a trick how to remember that easily. No. Take the open loop. So take R of S times G of S. And in case of a PI controller and PID controller, this R of S comes with a pole itself. It's this one. And then you draw the pole zero map of these two together. If it's a PID, you might have here, here, here. And then you just start canceling with the second pole. And then you go to the left. See? 1, 2, 3. 1, 2. So the second one is always correct. The only trick is you need to consider your controller with it, because a PID comes with a pole at 0. So you only need to remember number 2 and you will always be right. In my exam, if you cancel the first one, it's also going to be fine, right? So I really usually have 2. What you should not do is cancel the fastest one, because then you basically don't have any effect. So for a PID controller, you don't need to think, cancel out the slow ones. For a PD controller, maybe take the second one. Okay. So we already used now, when we think about the PID controller, 2 of our 3 free parameters. And what's left is this KPID, right? There's still the gain of the controller. And we can use that gain, for example, to set the damping of the dominating pole pair, or the frequency, whatever you like. But you could have other interests, like limiting the control command or reference tracking or whatever. In this lecture, we are mainly going to use it to set the damping of our system. But in practice, if you're ever going to go into controls and look back to that lecture, you need to be aware of the fact that you can use this gain. It's another free parameter for what you like. You can speed up your system even further. You can shoot for an optimal damping, 0.7. You can set a frequency. You have one free parameter, so you can tackle one additional design requirement. Okay. Most of the time it's going to be a combination, and yeah, this is usually the way in control what it is. You have too many design requirements and too few free parameters. So it's going to be most of the time a trade-off between design criteria. Okay, that's basically it for the introduction of the pole zero cancellation methodology. And now I actually want to apply this methodology on the espresso machine. And I really promise you it's the last time you will see the espresso machine example, because I figured students get fed up with the espresso machine. But in my opinion, it's so simple that I always can refer to that, because everybody knows what an espresso machine is doing and how it's working. Okay. And for that espresso machine, we're going to do a controller design based on the pole zero cancellation method, and we're going to go through a full design cycle. I don't think we're going to get through the whole thing today. We only have like 25 minutes left. But the design cycle is basically a modeling part and the design part. The modeling part I'm going to show you. Although I promised you don't need to do modeling in this lecture, you don't need to do it. But as a lot of you have done this practical exercise, I think it's important to see what's behind, and usually it evens up things a little bit. Yeah. So what we're going to do is we're going to model this espresso machine, and I actually show you what's behind this Simulink model, and then we're going to design a PI controller to get steady state accuracy and set the damping to 0.9. But first, we're going to start out with the modeling part. So we want to have our espresso machine, which is this guy here, modeled. So this is our G of S, basically, right? So forget about the controller for a minute. We're going to use that later, and we're going to discuss that. Now we actually want to understand what this model is. And if you remember, this model has, or this espresso machine has basically a heating element. Is this guy? It has a boiler where our water is. So this is water, and we have a thermometer to measure our temperature. This is this guy. Okay. So when we talk about the heating element, okay, what are the things to look at, so to say? The heating element has a certain temperature, right? What we plug in is current, basically. So we put in a certain we put in a certain power in kilowatts. This power is then transferred into a temperature on the heating element. The heating element gives energy to the water and thereby heats up the water, right? And obviously this thermometer measures that water temperature. So if you want to model that guy, and we call that X1, which is the temperature of our heating element, and it's basically, when you remember thermodynamics, is this capacity here, and the change in temperature of the heating element is wrong line. Yeah, it's actually the so-called Joule heating. This law, this physical thermodynamic law, it's actually a little bit also from electrical engineering, describes how an input power is transferred or is transformed to temperature. You can actually Google that and find some interesting stuff about it. What's interesting from a system dynamical point of view is that this is a purely integrating system, right? What that means is if I have a constant input power, my water temperature always gonna heat up. It heats up until it reaches infinite, right? Obviously, we know from engineering this cannot be true because we have some energy loss, right? So when we put in constant power of 0.25 kilowatt, our temperature is gonna end up at a steady state value and not run to infinity, because we are losing some heat to the outside, right? And there comes the so-called heat transfer into play. And it's depending on the capacity of the heating element and basically on the temperature difference between X1 and X2, where X1 is the temperature of the heating element and X2 is the water temperature. So you have some, yellow is not good, you have some energy exchange between the water and the heating element, and this is what you see here, right? So just for double check, if the water temperature is lower than the temperature of the heating element, we are losing energy to the water, and the temperature gradient, so X1 dot, is negative, right? So the water temperature is lower than the temperature of the heating element. This guy gets negative because X1 is bigger than X2. Our temperature gradient of the heating element is negative. So we're it gets colder because it heats up the water. So that makes sense. Okay. As I convinced you, hopefully, we don't like ODEs. That's why we're going to do a Laplace transformation. And if you do that and bring that x1 to the other side and divide it through, you basically end up with a transfer function of Ku over S plus this kappa heating element times U of S plus kappa heating element over S plus kappa heating element times x2 of S, right? And actually got some numerical values. This Ku is 210 and this kappa heating element is equal 5. So what it also says, tells you is that this guy is pretty big, so obviously you don't need a lot of power because this heats up very fast, right? So this Joule heating is really dominant in that model here. Okay. Yeah. The problem here is that we are actually, as engineers, are more interested in the input-output behavior, right? So what we are interested in the input, in the power, and what comes out is the water temperature. So we somehow will need to get rid of these x1s and x2s. Okay. So this was the heating element, but we also have the boiler. Okay, how does the boiler look like? So how is the water temperature changing? Well, the water temperature is changing by the heating element, right? It's basically the other way around than before. Obviously, if the water temperature is lower than the temperature of the heating element gradient here is negative because it loses temperature. The water temperature must heat up, so we need the reverse here, right? We had x2 minus x1 here, so we need x1 minus x2 here. But we are also losing some energy to the outside, right? We have here an outside temperature of 0 degrees. I put it to 0. I will explain in a minute why. But let's say it's 0 at this point. We are losing temperature to the outside. So we again have a heat transfer to the outside. This Ku is basically tells you something about the isolation. And we have the Tu, which is Umgebungstemperatur, that's why this is U, minus x2. Again, we are double checking the sign. If the outside temperature is lower than the water temperature, this guy gets negative, and we have a negative gradient on the water temperature, meaning that we're losing energy to the outside, our water temperature gets lower. So we're going to assume this guy is constant, and we're going to assume it's equal 0. If it's not equal 0, like it's 20 degrees, it doesn't matter. A linear system is always around your equilibrium point, right? So if it's not going to be equal 0, but 20, like we had in the example, we need to set initial values to all these integrators. So for this exercise here, it's most easily to set it to 0, so we don't need to always take the initial value of our ODEs with us. The behavior will not change though. Okay, so bottom line, it's 0. Okay, we do the Laplace transform, we bring it to the other side. We have x1 is equal kappa O for Oberfläche over S plus kappa O plus kappa U times x1 of S. And some values, kappa O is equal 3, kappa U is equal 0.3, and Tu, we said it's going to be equal 0. Okay, so we have now modeled our heating element and our boiler, but obviously there's some kind of connection, right? Because the water temperature, which is the output of our boiler, goes back to the heating element. There's some interaction here. If you look at that figure, that actually looks like a control loop, and most of you or actually all of you who sent me the first exercise did it correctly. This is actually, you can see that as a control loop, but in reality it's just a physical system, right? But there's also some loop interconnection between the heating element and the boiler, because you take the heating element and plug it into a boiler. It's like a feedback loop. So that means basically for us that we can get rid of this X1 here, but because we are not really interested in the temperature of the heating element, and we simply plug the equation into each other. Okay, I'm gonna probably on the next slide, I'm gonna write down the equations we have so far. The first equation, this is just a recap now. X1 of S is equal Ku over S plus kappa heating element times U of S plus kappa heating element over S plus kappa heating element times X2 of S, and we name that equation 1. Our equation 2 was X2 of S is nothing but this kappa O over S plus kappa O plus kappa U times U of S. So we name that equation 2. So to get rid of this guy, we simply take the second equation. No, to get rid of X1 first. What was X1? Let's look back. Yeah, we said we want to get rid of X1, the temperature of the heating element. We take equation 1 and plug it into equation 2. Oh, this is the error. Here it's X1. So now it's correct. Sorry for that. So we take that guy and plug it in here. In that way, we get rid of the temperature of the heating element, which we're actually not really interested in. Okay, so I need to do this now. Let's do this a little bit because I need the space. Okay, this is basically just pure algebraics, right? Okay, of S is equal kappa O over S plus kappa O plus kappa U, and then we plug in X1 here, it's Ku over S plus kappa heating element times U of S plus kappa heating element over S plus kappa heating element times X2 of S. Okay, so what we want to do have is we want to have X2 is equal some transfer function times U of S, right? So we need to bring X2 on the other side and then divide it through. Okay, let's do this. So if we bring that to the other side, it's X2 of S bracket 1. We multiply this out. It's this guy times this guy. Bring it to the other side. It's minus. Okay, kappa heating element over S plus kappa O plus kappa U times, and this guy here is S plus kappa heating element. And on the right hand side, our U remains, so we've got this guy and we've got this guy. So we've got kappa O times Ku over S plus kappa O plus kappa U. You will have the nice version in the final script, or you actually already have it, right? Because I uploaded it. Times U of S. And then we simply need to divide by this guy. Okay, I did that already. I'm saving a little bit of time, and you get out, what you get out is kappa O times Ku times S plus kappa O plus kappa U times S plus kappa heating element minus kappa O times kappa heating element times U of S. So this is transfer function of the espresso machine. Question to you in the chat, what system behavior do we have here? Anybody has an idea? Nobody? Well, this is a PD2 system, right? PT2. If you multiply that out, this guy is constant. You got some S squared proportional because of the denominator. Yes, proportional. Perfect. And we've got a second order lag here, right? Because we've got an S squared here. So it's a PD2 system. So the clue is, this is the espresso machine alone without sensor. And if you remember the first lab exercise, we actually said we identified a PD1 system. And now I'm telling you it's a PD2 system, and we will see why this was possible. And it is actually a PD2 system, but one of the time constant is so fast that you actually don't realize that it's a PD2. When you look at the step response, it looks like a PD1 because you have this very big time constant dominating your system response and this very slow, fast one, which you barely see. This is why, really, if you look at it, looks like a PD1. So you could say, oh, we did a mistake. Well, we said we do an approximation, right? And if a system looks like a PD1 system, but it's actually a PD2, we can consider it as PD1 system because this fast time constant is, this eigenmotion is basically going away pretty quickly, so it does not have a lot of influence as long as it is stable. So it's a good approximation, or this is what you do in control, right? When you say, okay, I have a high order system, but only one eigenmode is dominating my response, I can approximate that system with this low order system because we will see controlling the system then is much easier, at least for the design. Okay, so PD2 system for the espresso machine. The thermometer is a classical PD1 system. And it looks like this. We have a time constant times our y of t plus y of t. And now we are actually introducing y of t, the output. The measured temperature is our output. Remember, if you go back, this y of t is the measured water temperature is our output of the system. And obviously it takes in the actual, the real water temperature. So there is a small time delay between the real water temperature and what we measured. Kind of makes sense. What it's notable here is that you should have a 1 here, right? Because it does not make sense that if the water temperature is 100 degrees, that you measure just 50 degrees. Then you would have a 0.5 here. A steady state gain of 0.5 does not really make sense for a sensor. Okay. Okay, let's do the Laplace transformation. We get y of s is 1 over t sensor times s plus 1 times x2 of s. So now we can actually get our overall transfer function, namely we plug in equation 3 into equation 4. Remember, equation 3 was this guy. So we plugged it in and we solve it for, we plug equation 3 into equation 4 into here, and then we have our y of s. And our y of s looks like the following: ko times ku over, and now this whole thing again, kappa o plus kappa u times s plus kappa heating element. And we had some minus term here, which was kappa o times kappa heating element. And then we simply multiply it with the sensor. 1 over the sensor times s plus 1 times u of s. Yes. And finally, I added the numerical values, and you end up with a transfer function of y of s is equal 630 over s squared plus 8.3 s plus 1.5. So this is really just adding plain and simple all the values, and I think I computed this polynomial, which ends up being s squared plus 8.3 s plus 1, and what remains on the right is, oh, I think I forgot this, t sensor is 0.5, so we have 0.5 s plus 1 here times u of s. So this would have been a classical modeling process of the espresso machine, and actually me and my colleague did that before when we constructed the example, right? But this is what is behind the espresso machine. Now the actual job for a control engineer begins. Now we need to discuss the poles and the zeros of this guy, and this is the last thing we're going to do today. And next time we're going to do the control design for the espresso machine, and hopefully finally after 2 months reach 96 degrees. Okay, so what are the poles? Well, if you want to compute the poles, you basically need to solve this second order polynomial and this one, right? So this one is pretty simple because this gives a pole of -2, and the other one are also not that hard. So our P1 is -0.185, our P2 is -8.12, and the pole from the sensor is -2. We know how to convert that into time constants. To be fair, time constants are usually a little bit easier to interpret, at least for us as engineers. So you take the negative inverse, this is 5.4, and remember I told you in the lab exercise, these are actually minutes, not seconds, right? This is how the model is set up. If we would have done seconds, the whole thing would have been like crazy numbers. So we said, okay, we're going to do the whole modeling in minutes. And -2 means a value of 0.5. Okay. So let's discuss this for a minute. We've got one left. The thing here is, you should realize that this guy here is the dominating one. And when in the first lab exercise, we basically did not consider this sensor, so we left out this one. If you take this couple here, you realize that one eigenmode takes 4.5 minutes. Yeah, it's a long day. 5.4 minutes, what means to reach 95% of your final answer. This eigenmode nearly needs 15 minutes. The other one is only 0.12 minutes. So for the second eigenmode, yes, a question in the chat, is it now a PD3? Yes, it is a PD3. I come back to that in a second. The other eigenmode is 0.12. So this guy reaches its steady state value of already after 0.36 minutes. So it's like a factor of 50 or something, right? So the first eigenmode will have vanished a long time ago, and the first, this 5.4 minutes really dominate your response. And this is why this is so dominating your response that we actually said, okay, we can approximate this with a PD1 system, and this is what we did in the first lab exercise. We looked at the figure and said, it looks like a PD1, so just compute this one time constant, and I think it was about 5.5, right? So we approximated basically our PD2 with a PD1. Adding a sensor, as the question in the chat is, adds another pole, adds another stable pole, so we are ending up with a PD3 system. And you see it here on the last slide. This here is a PT2 multiplied by a PT1 is equal a PT3. Okay. This is the explanation what we actually did in the lab, that we actually identified a PD2 system as a PD1 because of this pole here, which is so dominating. One final thing is, which I wanted to do is, I'll take this 1 minute and compute the final this static gain, right? Which is nothing but taking the final value theorem, letting s go to 0 for our transfer function, which we can write u over s, times, when we do a step input, it's going to be 1 over s, and it's going to be s for the final value theorem. So we actually just need to put in 0 for s, but I'm doing it slowly. S squared plus 3.8 s plus 1.5. And we've got 0.5 s plus 1. And if you set now s to 0, right, cancel this, you cancel this, it's going to be 420. Remember, in the lab, we put in 0.25 and it turned out to be 105, meaning that it's the same gain, right? Because 0.25 times 420 is exactly 105. What it means is, for 1 kilowatt of power, we get an increase in water temperature of 420 degrees Celsius. Okay, so much for the system. Next time, we are actually starting with the control design. I'm going to recap that slide, talk about a little bit about the system, and then we continue doing the PID, only a PI controller, and we will see, should be kind of clear which eigenmode it is a good idea to take out of the equation here, namely this dominating one, which nearly needs 5 minutes to get to 36% of the desired water temperature, right? Okay, sorry for the short delay. Have a nice week. Bye-bye.